Hello, everyone. It's me, Billy Younger, again. This time we're doing Special Relativity 004. So in 001, we basically introduced the concepts and derived time dilation. In number two, we did some quick calculations of various beta values for a given gamma factor, which is basically the factor that something uh, time dilates by or something Lorentz contracts by or length contracts by that gamma factor. And then in special relativity 3, we actually derived the expression for length contraction. Now we're going to actually see some of those equations in action by solving a problem about muons. Muons are created in the lab in many ways, but in everyday life at the top of our atmosphere, up around 15,000 kilometers above sea level, we have basically the solar wind coming in with protons of high energy, and they will run into the atomic nuclei of various molecules in our atmosphere, and that actually can produce muons. And those muons are traveling at a very high speed and end up at the surface of the Earth. So I basically make up some extra digits and some numbers, but use rough estimates of the real numbers to let you see some interesting facts about the muon. So let me start by sharing my screen so you'll see what the problem is. So here's the problem. When high energy protons from our sun hit the atomic nuclei of molecules of our upper atmosphere, the collisions frequently release muons. These reactions are mostly thought to take place at around 15 kilometers above the Earth's surface. Remember, that's 15,000 meters. And the resulting muons are found at the Earth's surface with a velocity of 97.393% the speed of light. That's where I carried some extra digits. I was trying to match basically an energy that I found, and that worked out this way with that many sig figs. If the lifetime of the muon is 2.2 microseconds, how far can we expect the muon to travel during that time if we ignore relativistic effects? So let's go ahead and take that into account. Let's just ignore the fact that we know because this thing's going to be moving towards us that we would expect its lifetime to not be 2.2 microseconds, but to actually be time dilated by a gamma factor. In this case, we're going to just pretend like none of that happens, and we're just going to say, okay, let's calculate how far it should travel. So let me start by doing that. And notice this is problem number 3. And I'll turn it on my document cam. So this is problem number 3, part A. Basically, what we're asked to compute in this case is how far we think it would travel. Well, we know that velocity, at least the average velocity, is distance traveled divided by time taken. So from that, we know that distance traveled should equal velocity times time. Well, I'll say delta t there. So velocity times time. So if we ignore the fact that this time is going to expand and stuff like that, we can just take off this and actually compute the distance as 0. And remember the figures that I gave you was 0.97393 times the speed of light, which is 299,792, or excuse me, 299,792,458 meters per second. I'm just writing that out for concreteness, and 2.2 times 10 to the 6 seconds. That's the total calculation. Again, I wouldn't need to write this number of digits for this problem. I just did it just again to remind you that this is the actual figure and that this figure is really now set up so that the second is defined in terms of it. So it will never change. Okay. When I do that calculation, I end up finding out that delta x is in fact, and y'all should always check me on this work, the distance should be 642 meters roughly. Okay, so I'll just call that 642 meters. I'm really only using 2 sig figs, so I should underline that and just write that as meters. And that, of course, is the answer to part A. Okay, now we'll turn back to our problem and look at part B. So again, I'll share the problem on my screen. And it says in part 2, what is the gamma factor at this speed? So we now know this huge speed, and we roughly estimated what distance it would travel if no relativistic effects were going to happen. Now we're asked to find out what the gamma factor is. You're going to be impressed. It's going to be a quite high gamma factor. So let's do part B now. Again, stop sharing. Now part B, gamma, of course, is defined to be 1 over the square root of 1 minus v over c quantity squared, which in this case, you notice the v over c would be 0.979, 97393 times c divided by c. So really all I have to do is put in the 0.97393 because this really is beta. So I'm just going to do 1 over the square root of 1 minus 0.97393 squared. And I'll do that calculation. And roughly what I'll get is about 38.8. Now, obviously, I could carry a lot more significant figures here, even though I just made up all those extra digits anyways, just for the problem. But 38.8 is a pretty significant gamma factor. That means, for instance, if a 10-minute ice cream cone was traveling at this speed, we would observe that ice cream cone to not take 10 minutes, but to take 388 minutes, basically. So that's obviously a really, really big gamma factor. So now we start with part C. So I'll again turn back to our problem, share the screen. And with part C, it says, how long will we, watching the muon fly towards Earth, think the muon lives? So in this case, I'm actually dropping hints in the problem. I'm saying, how long will we, us people that are watching the muon fly toward Earth, think that the muon lives? What I'm saying is, hey, we're actually going to see that time dilated. So we need to calculate that dilated time. Now, both the birth of the muon and the death of the muon occur at the same place, specifically at the location of the muon. So that is the actual proper time. What we're measuring, though, what we're asked to calculate is the dilated time. So the proper time is the 2.2 microseconds, and now we're going to use that to calculate the actual dilated time. So what we know is that delta t is equal to delta t0 over the square root of 1 minus v over c squared. But remember, that's also about, or that's also equal to gamma times delta t0, which I think is a much easier way of writing it now that we have that gamma factor. So I can basically say that this is going to be roughly 38.8 times 2.2 times 10 to the negative 6 seconds. And of course, that turns out to be about 85.5. Again, using only 2 sig figs, there wasn't any use to carry more digits in this anyway. So 85.5 times 10 to the negative 6 seconds, or 85.5 microseconds, is the dilated time that we see. And that dilated time is equal to here. So we've now completed part C as well. Let's now turn back to sharing our screen and find out what part D looks like. So in part D, I said, given this dilated lifetime, so I'm again hinting back to what we just did in case you didn't get it the first time around. Given this dilated lifetime, how far should we expect the muon to travel before disintegrating? Is that distance sufficient for us to make sense of the muon detection at the Earth's surface? So now what we're going to do is we're going to actually see how long it should travel, given that it's actually going to live, according to us, 85.5 microseconds, traveling at that 97.393% of the speed of light. And they're asking us, is that really going to make the 15,000 meters or the 15 kilometers that we talked about? Well, what we know is that the velocity, again, is delta x over delta t. So the distance traveled, delta x, should be equal to V times delta T. And this delta T is really the time that we just used here. So it is correct not to put the little proper time down there. So what we know is this velocity is 0.97393 times, again, the speed of light, which you could use all those 299, 792, 458 if you wanted, but I'm just going to say 3.00 times 10 to the 8th meters per second. And then I want to multiply that by 85.5 times 10 to the negative 6 seconds. So you see that the seconds cancel out. We're ultimately just left with meters. And when I carry out this multiplication, I end up getting 24,953 meters. And of course, really, I'm only using 2 sig figs, so really that's extra digits for me. But that is actually going to be our delta x. So, in other words, that's how far we think it should be able to travel, thanks to its time dilation. And that, of course, is consistent with us seeing the actual muon hit the surface of the Earth. And, you know, we should be able to explain it from our point of view as well as from the muon's point of view, because if the thing actually collides with the surface of the Earth, for instance, we both have to agree that that happened. So let's now turn to part E. And part E, I'm going to go ahead and share the screen again so we can see what part E was. So part E, it says, if a who, as in Horton here's a who, began living on the muon the instant it was created, how far would he estimate the distance to the surface of the Earth to be? Does that sufficiently explain to the who why his home ran into the Earth? So, for instance, he's just jumped on the muon at the instant it came into existence. That's his new home. He knows that the muon's lifetime is only going to be 2.2 microseconds, but he's a little critter, so maybe 2.2 microseconds is a good period of time. And what we're asked to do is estimate how far of a distance he thinks the Earth's atmosphere to be. So in other words, he's actually out 15,000 meters or 15 kilometers up, and we want to figure out in his reference frame where the Earth and the Earth's atmosphere is moving at it at 97.393% of the speed of light. What is that 15,000 meters or 15 kilometers? So that's really what the problem's asking here. So let's work it out and see. So what we know is that again, the distance in this case, which is actually going to be a distance that's moving with respect to the muon and therefore the who. So it's actually going to be the non-proper distance, L, and L is going to be the proper distance divided by gamma. We already know that the proper distance is 15,000 meters, and we also know that gamma is about 38.8. Again, that's a dimensionless quantity. So just dividing that out, what we find is that this 15,000 meters or this 15 kilometers is more like 386.089 meters. So well under, this figure right here is way smaller than the time that it could actually make it. So we see again that this who agrees that the travel could be made in its lifetime, and therefore we can now confirm that the muon must in fact hit the surface of the Earth, and it's explained from our reference frame, from the Earth's reference frame, as a result of time dilation, making the muon tend to last a little longer. On the other hand, from a muon standpoint, what he sees is that the 15,000 meters isn't 15,000 meters, but rather is 386.089 meters. And of course, if you take his lifetime and multiply that by the velocity of the actual atmosphere, then you'd say that delta x is going to be 0.97393 times 3.00 times 10 to the 8th meters per second. So that's the velocity that he sees the Earth and its atmosphere traveling at him with. And then, of course, he knows his life is 2.2, or his muon's life is 2.2 times 10 to the negative 6 seconds. And when we compute that, we're going to get 0.97393 times 3 exponent 8 times 2.2 exponent negative 6. And lo and behold, we get that 642 meters again. 0.793794. Again, we're using way more sig figs than are really necessary. So you can see this is actually the original bit that we thought without length contraction and time dilation. That's actually the same distance traveled, because that distance is in fact farther than this. Then both us and the WHO agrees that the muon can make it to the surface of the Earth, which is good news because we know it happens. And that, of course, is a wonderful piece of evidence for the special theory of relativity, because it confirms not only the time dilation formula, but it also confirms the length contraction formula, because you actually need both to explain it. I hope that helps. Have a good day.